All right, everyone. So apologies for the perturbation in the schedule today. Can't be too cautious, and everything should be fine for Monday. We'll be meeting together then. But today's lecture is entirely online. I'll try to write in big letters. And to that end, we are still in our early stages of Dirac notation. Remember that Dirac notation is a way to do quantum mechanics minus a lot of the math. Not entirely, but a lot of it. We represent a state by a ket. And when it comes to, we're going to stick with electrons being spin up or spin down. But you have to think of directions, right? The direction of the Stern-Gerlach experiment that measured spin up versus spin down. The magnet simply, you don't have a choice about this. You have a bar magnet, and it has to be pointed in a direction like Z or X, and we can't really do Y, but we can still figure out what that looks like. So again, we all know that electrons are either spin up or spin down. You saw a consequence of that, which is that if you shoot an atom which has one excess unpaired electron, the paired electrons don't have any magnetic properties. The unpaired does. And it can only deflect up or down, as though it's only fully oriented up or down with respect to the bar magnet. A little weird because we think of a vector as being pointed with any direction, and again, this is something I can't explain. There is no classical analog to this, but this is how it is. And so we have a ket to describe the state of that electron's spin angular momentum being pointed up. Recall that we also are going to, not so much right now, but I want to ease you into this. We have a matrix to represent these states. These are pretty important. They're called Pauli spin matrices, by the way. Kind of. We're going to build up to what are called Pauli spin matrices, and so it gets you used to how matrix mechanics works. Often you may have heard of quantum mechanics referred to as matrix mechanics. Most quantum mechanical problems can be put in a matrix form, and that's great because it really is way easier to do the mathematics. Whereas personally, I like kets. I like kets for visualization. I understand the state of matter better when I see a ket. But I've already taken this class, so it's easy for me. Okay. Now remember that one of the most important things about quantum mechanics is that a set of states spans Hilbert space, right? Now what that means is that had I pointed the magnet, the bar magnet, in the x direction, the ones that move in the plus direction, whatever plus is, I don't know, but you make a decision and call that plus, can be expressed as a linear combination in the z basis. So you need to get familiar with the words I'm using in the basis of the z states. And that's what it means for them to span all space, is that I can put any other state, I can use the z states to represent that. Plus or minus in the x direction, and that's all there is. And since that's all there is, the two states, plus and minus in the z direction, span all space. Here we go. Okay. And I'm not going to write down why, but it's the same thing with the letter I, and basically same idea. Okay, and these can also have matrix representations, and again, in about a week, you're going to really appreciate this. It is way easier to do all of the more mathematical problems with matrices. You don't have a choice on many of the problems, actually. Okay, so again, I just want to get you used to these represent states and the way that a particular combination can represent all space. So if you followed that far, that's great. Okay. And of course, these are related to wave functions, but we're going to have to take a little bit of time to build up to that. And let's see, now, of course, quantum mechanics also has operators, right? You have states of matter and operators that report on that state of matter. So again, I'm still reviewing from last time. Now, operators, you had undergrad quantum, and operators spit out the momentum as long as they work in an eigenvalue equation. They spit out the energy if that operator was the Hamiltonian. But now here's the thing. Most of the operators we're going to look at correspond to observables, and observables can be measured, so therefore I can actually associate like equipment, like the experimental apparatus to an operator. That's an interesting way to think, and actually a really good way to think, because what you're going to see is that measurements change things, right? And that's some of the more popularized, some of the things you hear about quantum mechanics in popular literature is that you can't measure something and change it at the same time. Sometimes measuring something will destroy something. That's another way it's expressed, but that's a little inaccurate. Okay, so we talked about a Stern-Gerlach measurement in X, which puts something in the plus X direction, just because why not? And I can I can then pass the beam of silver ions to a bar magnet in the Z direction, and I can block the ones that are minus. And so this ends up being in the plus Z. Okay, so we filter things to the plus X state, and then we filter them to the plus Z. Well, this is basically an operator. And my generic, it's a very generic representation for an operator to say this. H is the Hamiltonian, right? So that one's special. Okay, now what is this operator? Well, it looks like whatever it's doing, it's turning states, no matter what the input is, the output is a Z plus state. So I'm going to call this a projection operator, and it's a good introduction to operators, although you've seen operators before, but when we're doing this plus or minus thing, this is a good one. It's easy to understand, and when I operate on the SX plus state, what do I get? I am going to just go ahead and write down the answer because it basically looks just like, I forget these commas, if you put the commas on the word will explode. It's just basically the commutative axiom of algebra, essentially. So, oh wait, no, I did that right. Let's see, then I've got this. Let's see. Plus, now remember, this is called a bra. We'll be talking more about that today. I have to look at what happens here. And when I'm forming these are called inner products. Okay, so I take this bra and I abut it next to SZ plus. And that's here. That's the same thing. That ket I just wrote is right there. Okay, then I'm going to get the same thing again. That also, this is what we call a linear operator. You know, I stand in the way sometimes when there's no one in here. I've had to lecture plenty of times to an empty room in the past several months, and I notice I stand in front of the, oh God, I've run out of the room. What have I done? SZ plus, SZ minus. Little comma. The comma needs to be in the right spot. Okay. All right. Now, these are called, we have a word for this, it's called an inner product. There it is. You don't need to memorize that or anything. And it's not hard to figure out how this game works. So in terms of the rules of Dirac notation, this is basically rule number one, that when you see something like this, it's 1.0. Right. Now, you can also prove this with like integration, because quantum has integrals everywhere, so where are the integrals? Remember, I can show you an integral representation that turns into the number 1.0 in about 2 weeks. So you're going to see that in about 2 weeks. Right now, I'm just telling you it doesn't matter. This is 1.0. Okay, now this is a bra and a ket, and they are completely different states, and that's going to be 0.0. So I think you can look at this symbology, and it kind of just intuitively makes sense, and that's awesome because not much else does make intuitive sense with quantum mechanics. That this bra and ket being the same thing is 1, and when they're different, they're 0. And yes, that's exactly what's going on. Okay, so let's see here. And I'm going to get more into this, why this is. I'm just giving you some examples, and remember, we're also trying to develop on the rules of Dirac notation such that we can generate the results of the Stern-Gerlach. So we're developing a new mathematical representation that, for one, is quantum mechanical and reproduces this stuff here. So that's our goal. Okay, now I've been talking about Sx and Sz and Sy, but in general, okay, you may not know what a state is, which is basically what's happening when you're doing an experiment, right? I've been assuming everything, or I've designed everything such that I know exactly what I'm dealing with, but that's not going to be practically true, like ever. So now that you see that the kets Sc plus and Sc minus span all space, you know that there's no particular electronic arrangement for like silver, something with one excess electron that can't be represented as a linear combination of Sc plus and Sc minus. Let's see, what else I want to say. And that means that if I was to operate on this with our projection operator, the results again, I think it's pretty intuitive, right? So the projection operator is going to end in the Sz plus state. So my input is some unknown state in terms of where the electron is pointed up or down, or left or right or backward and forward. I don't know what state it's in. But if I run it through this apparatus, what's going to happen is you're going to get the projection. You're going to end up, so you see how a measurement changes the thing. Your final state is going to be Sc plus. So the original state is destroyed. The final state is Sc plus. That's again the effect of the Stern-Gerlach apparatus, which is represented by this operator. And the amount of material that comes through will be this overlap. Where am I in my own nose? Okay, so now we see a little bit of a less intuitive inner product, and what this ends up being is, and I'll write the coefficient out front. It's a little bit more natural to the way we represent mathematics. Put numbers in front of functions, so that's this represents a state. So we're used to numbers being out in front. C is of course a number, 1/square root of 2 or something. It can be complex. Remember, in the case of Sy, we're avoiding Sy for multiple reasons, but the coefficients could be complex. And now one reason that's okay is that observables are always the square of everything. Absolute squares. And absolute squares means that if there's an imaginary component, then it's not a problem. It goes away. Okay, now, let's see, what else do I want to say? Okay, I got more rules for this stuff. Let's see, what do I want to show you? I want to show you this. Let's do a matrix representation, because again, this is going to be real easy, but we're going to be getting into this quite a bit more, so I'm doing baby steps here. I'm not following the book, by the way. The book doesn't show you this early on. Okay, so we see that in the operator we have a ket and a bra up there, ket and a bra. So let me show you how to represent a bra. Instead of a column, if you noticed, I had written column vectors for kets, 1, 0, 1, 0. But a bra goes the other way. So Sc plus is going to be 1, 0. Now the reason that's important is that if I'm representing in a matrix representation, if I want to represent this inner product, which again is like the overlap of this state with that state, which of course are well known, what you end up with is, okay, that's 1, 0, and I'll bring that square root of 2 inside of the column vector, that row vector, column vector, in case you forgot. In that middle school, right? Or maybe high school, I don't remember where I learned matrices. And if you had forgotten once you, in case you forgot how to deal with this stuff, usually just a little bit of review, look on Wikipedia, you remember pretty quick. Here is the first, so you're going to end up with the column vector. Here is the first element. And then here is the next element, which is 0 times square root of 2, which is 0. So this is basically SC plus. It's diminished a little bit. Kind of like how in the Stern-Gerlach experiment, right? So like I say, things are a little diminished a bit. It's because some of your atoms get chewed up in the process. So the amplitude of the state has been decreased a little bit. And that would represent, that physically means that you chewed up some atoms in these little beam blocks that we have. So all of this is meaningful. You can think of experiments to represent all this stuff. Okay, a little bit more about kets, and then I'm going to get a little bit more to bras. Now, hopefully kets are kind of, very intuitive. They're basically wave functions, but not quite. I'm going to get into that in about 2 weeks. But bras may be a little bit more complicated. Now, hold on, let me talk a little bit about kets. We can do things like this. We're going to do this a lot when it comes to proofs. So we're going to prove a lot of theorems in quantum mechanics with Dirac notation because you don't want to do it any other way. But we can do things like this. We can take a state. This is like SX, sorry. This is like SX, where I've represented it with 2 kets. But you can just represent that with something else. We're going to do that as just kind of a good bookkeeping trick when we're doing a lot of derivations later on. So look out for that. Okay. Multiplying a ket times a number is just basically scaled. You're basically scaling a vector in the alpha direction. Now, I often say when I'm teaching Quantum 1 for PChem 2, Intro to Quantum Mechanics to undergrads, I always mention, I don't know if I should, I always mention that there's multiple words in quantum mechanics like wave function, eigenfunction, eigenvector. I want them to know that that word exists, but I try never to use it, but in this class, guess what? I'm going to use it all the time. Just like, now you can see why it's an appropriate word. I'm talking about spin in the x direction, z direction, and y direction. Well, you want to think of those as vectors. So the state is basically a vector in x, y, or z. So now you can see why I'm using the word eigenvector quite a bit, and will be in the future. Let's see. And again, this is just kind of like scaling it. In our Stern-Gerlach, that represents monkeying up the population in one of these devices for obvious reasons. Okay, so kets, again, I think kets are just really intuitive things. They're easy to work with, but now you've got the bra. Okay, so bras. Now, bras are largely, the book doesn't really provide an explanation for what a bra is, other than to say, I'll write down what the book says, because I kind of have to. So bras have a dual correspondence. Dual correspondence with a ket. I find that meaningless. I mean, I could define a theorem or something in French with a French word, and that doesn't really, I may have defined it, but that doesn't really help, does it? Okay, so learn by doing. All right, now the representation of this is like this. And again, I don't find this helpful. But what happens is, as we start to work problems in quantum, problems like this, you figure out what bras are by doing. Right, by answering questions over and over again, you'll figure out what their purpose is. And usually it's to project a state into another state. And why you might do that, well, in this case, we have a little example of the Stern-Gerlach experiment, why. And after you've done maybe 1,000 other examples of bras and kets working together, you'll figure out what their function is, again, by doing. So anyway, this is a representation of a dual correspondence. Now, as I just mentioned, we can have a state, a gamma state, which is really a combination of two other states. And so they are dual to, and again, in terms of like, well, what does this do? What does this mean? It means nothing. To be blunt, it means nothing. Or I haven't figured it out at least, it's probably more accurate. What is meaningful is this. Okay, this one's important. If we've got a number that's scaling a eigenvector, and that's the ket, obviously, it is dual to this. And you really need to know this one. So when we do our proofs, oh, what the heck is wrong with me? The whole point is to go the other direction. Okay. Okay, now this is truly important. Dual to a scaled ket is a scaled bra, complex conjugate. Do not forget that. You will not be getting half your homework questions on the next two problem sets if you forget that fact. So put a star by that. Obviously, this is kind of painful to write this down, but maybe you don't need to write this down. I can take a linear combination of states, of ket states, and say that they're dual to the corresponding bras. Again, when it comes to this stuff that I'm writing down, I'm kind of obliged to write it down. But now, other than remembering that you have to take a complex conjugate when you flip from one side to the other, again, hideously important. When it comes to stuff like this is like a linear type of operation. You can kind of just guess that would be the case and you'd be right. So sometimes things are a little bit easier than you think. Let's see. Now, when it comes to inner products, I apparently cannot spell product. There we go. When it comes to inner products, and I'll just be a very generic beta alpha. Let's say that's beta alpha. Okay. I showed you two examples. SZ plus onto SZ plus is 1. SZ plus on SZ minus 0. Again, kind of intuitive. It turns out that an inner product is always a number. Okay, that one's important. Not a function, it's always a number. A number. And can be complex about half the time. Okay, remember complex means that you have a situation like A plus IB. So there can be a real, when you say that a number is complex, it can have a real and imaginary component. It doesn't mean that it's entirely imaginary. It just says, when I say a number is complex, it just says that there's an imaginary component. But of course that imaginary component can be 0, meaning it's all real. And people will use that sometimes. They'll say a number is complex even though all their numbers are real, and that comes up in a lot of proofs. Anyway, that's just really annoying, no doubt. Okay, now this one's important. This one's pretty important. Okay, I'll work this one as I go over bras. That's okay, inner product. Let's see here. Okay, so yeah. Again, this one, I know this is important because I wrote your homeworks. And there's one in particular where you have to do a proof about how to deal with bras and kets and taking complex conjugates, because you already know enough to know that comes up a lot. And if you don't know it, well, it's going to come up a lot, so now you know it. Okay, now this one's important. Again, you really just got to be careful about complex conjugates. That's what will get you. Okay, so I'll stick with beta. Okay, so beta is some coefficient of one state that's maybe related. Maybe this is a particle in a box state. Maybe that's the ground state. Maybe this is the excited state of the particle in a box. And these are states because they're kets. Okay, what I'm going to do, again, be a little careful. You can get a little confused what I've done here. That's a ket, but what I've drawn now is a bra. on the bra of beta, and I'm going to have that act on alpha. And hopefully you know that what's going to happen is that the coefficients, the scalars, are now complex conjugates. Doesn't mean anything if they're real. And notice that, of course, I flipped the ket beta to a bra. And, of course, the same for C2. Beta to alpha. There we go. Again, just rules of Dirac notation. You will see. They'll make more sense as we go along, as we use examples of things that are real and we apply this stuff to those things. It helps you visualize it. And then, of course, it'll make more intuitive sense to you. Okay, more properties. Again, used on, there's this two problems on your next problem set that are just awful because you have to keep all this stuff straight. Okay, this one's important too. Now, I told you some of these are not important. This is one that's important. It's terribly important to remember this. When you flip a bra and a ket, you are making whatever it is. Remember, these are numbers. They're often complex numbers. It's now a complex conjugate. Again, hideously important. Okay. Now this is going to sound kind of stupid based on what I said before. I've drawn an inner product of the same state. Now, formally, I have to tell you that this is the result. It's equal to or greater than 0. Okay. Now, there's a lot to unpack here. I told you before that this is always 1. And I'm largely standing by that. Now, I knew I was going to say this, but I'm still telling you, when you see this, you should basically write down 1. Now, why does your book say this? It turns out that 0 if alpha is a null ket. In other words, it represents nothing. The issue I have with that is, why do you have a ket for nothing, right? Counter to this is that the idea of a null ket comes up in 1 or 2 proofs. So that's why they want you to see it. So heads up. Okay. Now, other than the null ket, why don't I just say it's either 0 or 1? The idea here is that knowing that kets are almost wave functions, almost, not quite, you know that they may not be normalized, which is a weird thing, right? Because remember that the deal with wave functions is, like particle in a box, if you center it from 0 to L, all the states, the ground state and the excited states, they're all sine functions. It's easy to figure that out, that they're sine functions. But that doesn't automatically make them normalized. It's easy to figure out on the simpler problems what the function, the gross function is, it's sine or cosine. But the normalization doesn't just come out of your mouth or brain that easily unless you do the normalization, which, guess what, is this. Okay. This is called, that's the inner product. Let me write it bigger. Okay, so again, I'm just making sure you know the definitions, the formal definitions, even though they're not really that important. This is called the norm. Norm. Two cheers. Anyway, so that's called the norm. And so therefore a normalized state, of course a state is a ket, is this. 1 over the square root. Okay. Now hopefully what you're getting out of this is you're seeing some familiarity with what you learned as an undergrad, some of the stuff that we covered a little bit earlier in this class, that again, it's easy to figure out that sine is a good wave function for a bunch of problems, but you got to do a little extra to normalize it. So, here's our normalize. So again, a state is always a ket, so now it's to normalize it. So again, getting back to here, I told you that this is 1, except in the case of a null ket, which you'll almost never see. The reason that the book says it's greater than or equal to 0 is if you're dealing with an unnormalized state. However, the thing there is, you should always be working with normalized states. Never screw that up. You can get away with it sometimes, but just don't, right? So in other words, this is basically always equal to 1. If you don't have your head up your rear end and are working with normalized states. So anyway, that's just why they do that. Okay, next thing. Operators. Now, I'm going to show you stuff about operators, and these will be kind of intuitive too. Like what happens when you have 2 operators, what happens when an operator works on A and B. It's all about the middle school, associative axiom of algebra, commutative axiom. Seems like there was another one, I don't remember. And this is all linear mathematics. And I've never really run into examples that don't work this way. I'm sure if I knew a little bit more quantum, I would, but I don't care. Okay, so linear operators. And of course, I will stick with my generic, that omega? I don't know. Anyway, that's my symbol for it, the generic operator. Maybe it's a Hamiltonian, maybe it's momentum. Okay. So the deal is, and again, this is intuitive, but I'm kind of like legally obliged to write this down. Okay, and I'm actually copying from the book, so I'm being a little inconsistent whether I'm calling something C1 or I'm using C alpha, and that's because I'll say that this state is composed of an alpha and a beta state. Okay, so the operator is going to operate on this, and big surprise, this is what you get. No weird complex conjugates or anything, so it's got that going for it. But I think you could have figured this out without me telling you that this is what the thing does. Okay, and that bothers me. It's not perfect. There we go. Oh yeah, there we go. All right, so anyway, you could have figured that out. All right, now we're going to get into something that I don't even know what to say here. What happens when an operator works on a ket? It's pretty easy. And we're going to go over that in a minute. But what about when an operator works on a bra? Okay, so this is a little funky. All right, so I've drawn you this operator working on a ket, and you can imagine that this is like momentum derivative with respect to x, and that's like sine kx, right? Good. That's 99% of what you need to know when interpretation of what you see in front of you. Okay, where am I going with this? All right, so that's like this. A state, and it's being operated upon. It's the derivative, which is basically the momentum, and the state is sine kx. Oh, I should put a normalization constant, whatever. All right, now let's do the dual of that. It has a dual correspondence with, there's our bra, but I have to do this. I have to put a little star, not a complex conjugate, a little plus. It's not the same. And this is the adjoint of the operator. Okay, so here's the point. These, when we operate, and again, you have seen a bunch of operators, don't forget that. I mean, you've seen a bunch of wave functions. Kets are not quite wave functions, but it's good to think of them that way now. But when you're working on the bra, you may have to change it. So that's the point. Now, how often does this happen? It's rare. It's usually true that the adjoint is equal to the operator to begin with. Nothing changes. Most operators are like this. So in other words, don't worry about it. If that's the case, the operator is Hermitian. And that is horribly important, Hermitian. As you're going to see in a moment, Hermitian operators are the operators of things that you can measure for real, like momentum, energy, angular momentum, anything you could ever probe in a lab That's quantum mechanical, that's molecules and electrons, that's the stuff we only care about in our world. Everything you can probe, in the instruments that you use to probe it, can be related to operators, and all of those are Hermitian, and that just means that this is true. Now I'm going to show you in a minute, that means that the corresponding observables, which is like, well, how is it spinning? How fast is it going? How much energy does it have? The corresponding observables are always real. And that means no complex component. So, now I do have some examples of where the adjoint and the operator, where the adjoint and the operator are not the same. There are some of those, and we're going to see some when we get into the harmonic oscillator. And those, they're called ladder operators, and they're some of the most important things. They're important too. I see them in talks all the time. So you do need to know that although overwhelmingly true that these are the same, they're not the same, and they're not the same in one type of operator called a ladder operator, and that is a hideously important operator. God, let's see here. Okay. Now I told you that Dirac notation is a time saver out the wazoo that you cannot imagine, especially when we get into some really tough proofs, like when we prove, we're going to prove the uncertainty principle. The equation for the uncertainty principle via something called the Schwarz inequality. And you are going to be thanking Dirac for Dirac notation, because it's going to be way easy to do that. It's impossible if you don't use Dirac notation. Here is, but I told you that there are aspects that are a little difficult, and other than remembering some complex conjugates, which really aren't that bad. Come on, at this point, that's not hard. Okay, this one's a little hard. All right, so more on operators. And operators are not hard to understand actually on kets. It's when they operate on bras, again, it's funky. Okay. Now, one thing to note, and we're going to do this with a lot of proofs, you really want to make certain that you understand what you've chosen the operator to work on. Do you want it to work on the ket or the bra? So we often represent that this way. We're going to say that the bra is going to hang out by itself, and the operator is going to deal with the ket. But we don't have to. We could say that the operator is going to work on the bra, and the ket is going to stay by itself. That is also a possibility, and you'll see those when you have to start doing some proofs. Okay, this is the tough one. That wasn't so bad. This is the tough one. Okay. Beta, operator, alpha. I can't remember if your book uses. I sometimes change some of the notation from the book just because I like it better. Okay, beta. What have I done? Sorry, my notes are a little funky. Okay, so now what I'm going to do is, as you've seen, the only times this get a little funny is when we start switching things around from cats to bras. All right, so I'm going to do some of that. I have to not get myself confused. Okay. Now you're going to see why I was saying sometimes you want to think of the operator working on one or the other. All right, in this case, I'm going to have the operator hanging out with the cat. Again, it's kind of like the easier case. Well, what I'm going to do is I'm going to flip it. Okay, so I'm going to take the adjoint. Okay, so the alpha ket is now a bra, alpha bra, and that means because I've associated the operator with the ket, which is now a bra, I need to take its adjoint. Okay, so the parentheses, of course, mean I'm associating it with that state. It's kind of important. Okay, well, you really have to turn the bra. You turn the ket to a bra, you better turn the bra to a ket, or if you don't, by the way, you're writing nonsense. It's scientific mathematical babble. You can't just turn that to a bra and leave that a bra. That's just nonsense. And this will make more sense when I show you how to translate this back into the thing you had more as well, the first part of this class or as an undergrad where everything's a freaking integral. Okay, and you can imagine complex conjugate. All right, so a bit of a mouthful. All right, so I've associated it with alpha. I decided to take the adjoint because I turned the ket to a bra. That's its dual correspondence. I had to flip the beta, and just kind of like an inner product when it's flipped, it's a complex conjugate. That's actually entirely what I've done here. I've basically taken the, after the operator does its job, you're left with an inner product. And so if you flip that product from a ket to bra and bra to ket, you're going to have to pick up a complex conjugate. So two things are happening. I'm messing with the operator, and I'm kind of like flipping an inner product. So that's why I see an adjoint and a little complex conjugate. Make sure you don't get confused between the plus and the star. Okay, and then I don't have to write it this way. I can just say that it's like this. So you don't have to have little parentheses or anything. And of course, the way I write stars is always screwed up. Okay, so, all right, now what do I want to say? Well, I'm thinking about this. Now, let me start telling you about, I don't know if I'm really going in the right order here. I'm just talking about, I got 15 minutes, all right. You know, I'm following the book here, and I don't know that I should, because now I'm going to show you what operators do. We've manipulated operators, meaning that we've messed around with these adjoints. And again, for most of the operators we deal with, the adjoint is the same as the operator. In other words, it doesn't matter. You don't have to worry about these adjoints at all, except for the one operators I told you about, ladder operators. You're not going to see those for about a month. Maybe a harmonic oscillator. So sometimes when I was writing my notes, I was thinking, maybe I should do this first. So we're on eigenvalues and eigenkets, which are the same as eigenvectors. My pen's about to die, so I won't write that. And you know, I know some of this may have been like, you know, what? So I was thinking maybe next time, if I'm teaching this class again, if they won't kick me out for doing a bad job, I should start with this because this is easy. So this is an eigenvalue equation in Dirac notation. Okay, an operator acting on a state, that being a ket, returns a number. So that's a number. I was using the letter C before. Now I'm using A and the ket. All right, so the ket is the same, so that makes it an eigenvalue equation. Just like we had momentum acting on e to the ikx, where e to the ikx was a wave function, equals h bar k times the wave function. This is the same thing. Again, it's a Dirac notation. So hopefully, you know, you have some comfort by familiarity. You're just not seeing e to the ikx, and the operator doesn't quite look like I minus ih bar derivative, which is momentum. But now the only reason that is because I haven't said what it is yet. The operator can be anything. We're going to have probably about 20 operators by the time this class is done. Okay, now, one thing that's important, notice I'm kind of using different notation. I have this little A prime. Now, what we're going to build up towards is that, what my implication here is that A prime is a state in a family of states. Now, that would mean, let me give you an example, particle in the box wave functions. So this would be like the ground state, sine pi x over L, right? That's the ground state. Sine 2 pi x over L is the first excited state. So that would be a double prime, right? And so there's an infinite number of these with an infinite number of little primes, and they're all particle in the box states. So that's a good way to think about this. Okay, so and now I have to write this down just so you know. So A is eigenket, eigenvector, eigenfunction. It's not technically an eigenfunction yet, but it can be. This operator with value A prime. Okay. All right, now let's do a bra. If this is the case, then let's do this. Now again, you need to be working with an adjoint if you're going to operate on a bra. And guess what? Complex conjugate and bra. So now this is an eigenbra of the operator. And let's see. And as I mentioned before, we want to think of this A as probably being in a family of states that are all defined to work with this operator. So again, my favorite example that you're probably sick of is that the operator, maybe that's a Hamiltonian, and the states are particle in a box wave functions. And last bit, let's see, I got 10 minutes left. No, I have 5 minutes left. Yeah, no, that's perfect. That's absolutely perfect. Okay, now what I'm going to do, I'm going to show you for the first time why this is actually useful. I'm going to do the Hermitian proof. I'm going to prove that Hermitian operators, those are operators that correspond to things that are real. Things that are real include momentum, energy. I'm going to prove that all the eigenvalues are real and that the states are orthogonal. Now, if you forgot what orthogonal is, that means that if I integrate the ground state and an excited state, you get 0. You know, the word is the overlap is 0. Now, the problem with that is that it's not that like one is 0 or the other is finite and vice versa. It literally means that when you integrate the two, that the result is 0. So let me show you. Now don't write this down or anything. I just want to make sure you understand what orthogonal is. Orthogonal functions would look like this. So here's like a Gaussian. And if I integrated that with the y equals x, if I integrated these two functions, the result is 0. So they're both positive over here, but anyway. So it's not like one is negative or the other is, one is 0 or the other is finite and vice versa. They're both finite, well, except for y equals x at 0. Other than that, they're both finite. But again, you can see that if you multiply these and integrate, the result is 0. And that is what it means to have no overlap. So we're going to prove that Hermitian operators have wave functions that have no overlap. Unless it's the state by itself, which of course is expected to be normalized. Now, I also want to point out again that the proof I'm going to do here is going to be unbelievably easier than if you do it with the traditional method, which is integrals out your freaking ears. All right, now recall that Hermitian means, I'm going to use the board a little bit here, then I'll finish the proof over there, and that'll be it. Hermitian means, and Charles Hermite was a mathematician. None of this meant anything to him. I think he died before quantum mechanics came around. He just noticed that there were mathematical entities that worked this way, and he made note of it. And later, it would become one of the most important things in quantum mechanics. I guess he never knew that. Okay, now what I'm going to do is this. I'm going to point out that the operator acting on the A prime gives an eigenvalue of A prime and the state, and that the operator acting on A double prime gives an eigenvalue of A double prime, and so they're eigenkets. Okay, now this is kind of BS-y, but I want to say something, and it's going to come up in a minute. I'm being very generic here, right? So everything's an A or a B and a prime and a double prime. What I'm going to set you up on is I'm going to tell you right now that it isn't necessary, it may or may not be true that A prime and A double prime, maybe they're the exact same thing, right? I mean, what does a prime do? What does it matter? They're both sine, I have to think again, sine pi x over L. They're both sine pi x over L, or maybe not, maybe not. I'm not going to make a decision. It can be either or. Okay, now here's the Hermitian proof. Okay, so let's do a bra acting on the adjoint. You gotta do it that way. Sorry. Let me do the cats first. No, wait, I've already done that. Yeah. Sorry. The problem is I get lost in my own notes sometimes. Okay, so I did the cats. That was my problem. Okay. That is equal to a double prime star. Again, you've already seen this. Double prime. Okay, and because that now here, remember that I'm only writing what I'm writing down right now because of the Hermitian property. I said that this and this are the same, right? That's the Hermitian property. Okay, now with that, what I'm going to do is I'm going to take A double prime bra, the same thing I had there. Now I'm going to act on the right with the ket. I always have to act on the right with the ket. Okay, now the operator acts on A prime to produce a number, which it's just a number. And so is this, and that leaves this inner product, right? The operation on A prime leaves A prime ket. And so now that A prime ket is abutted to the A double prime bra, and now you've got yourself an inner product. Remember that these are both two numbers. They're just two numbers multiplying. Because A, it's an eigenvalue, which is a number, and inner products we've already talked about are numbers. Okay, now I'm going to do it. Now I'm going to let the operator act on the bra instead. And so that's going to give me A double prime star, and actually I get the same inner product. Okay. 1, 2. Now what I'm going to do is I'm going to take 1 and subtract from it 2. And what do you get? Let's see. Okay. This minus this is going to be a little hard to follow, all right? So I'm not just taking this, but I'm taking the whole thing. Taking the whole thing. This minus this is 0, because this is the same thing, right? So this minus that, 0 equals, okay, let's deal with this thing. A prime, A double prime inner product, minus A double prime star complex conjugate, inner product, which is the same. Okay. And then, of course, I can factor that because it's the same inner product. And this is it. This is the proof. And I hope you appreciate this because it is nightmarish to do this any other way. Multiple steps, none of them makes any sense. Okay, that's it. Now, what did we get out of this? It doesn't look like so what? Here's what you get out of it. Okay, that's 0. Okay. The easier one to start out with is if A double prime is A prime. So remember, I told you I'm going to pull kind of a BSE trick. I'm going to tell you that those were actually the same state the whole time. That's fine. Then, what have I done? What have I done? This gets a little star. My bad. It's very important. A little star. Then, A prime minus A prime star. So I'm trying to say double prime to an A prime because I've said that they're the same thing as 0. And therefore, the number is equal to its own complex conjugate. And that is only true for real numbers. It's not true for complex numbers. Therefore, the eigenvalues of Hermitian operators are always real. That's hideously important. The eigenvalues of Hermitian operators are always real. Okay, now the one that you probably were kind of led to believe, if A double prime is not the same thing, if they're not the same state, okay, now there's no way, if these aren't the same state, those eigenvalues are not the same. Oh, right here, sorry. Those eigenvalues, those are not the same. And we can do that with an example. That's going to be easier. The operators is the Hamiltonian. Hamiltonians are Hermitian. They're always Hermitian. And we are dealing with the ground state and the first excited state of the particle in a box. Well, the energies are not the same. Okay, so this is not 0. So therefore, a double prime and a prime G inner product is 0. And that is orthogonality. Okay. So a better statement is actually not this. You want to use a Kronecker delta. Remember, a Kronecker delta, A prime, A double prime. A Kronecker delta is 1, equal to 1, if A prime is equal to A double prime. That was the case up here. It's equal to 0 if A prime is not equal to A double prime. That means that like first ground state and first excited state. And equal to 1, by the way, that's also normalized, right? That's what it means to be normalized. That's why I was telling you, I kind of don't like that previous statement I had to make about inner products always being equal to or greater than 0. They're 1. They're 1, okay? They're normalized. Don't be an idiot. Everything's normalized. And so if these are the same thing, it's normalized, and by definition that means that the inner product is 1. But if they're not the same state, it's the ground state and the excited state, then the inner product is 0. And that is the most important thing in quantum mechanics when it comes to operators. That is the case. And with that is it. I think it went 5 minutes over. That's okay because it's online. And we're going to go quite a bit more. We're going to start doing proofs with this next time, which is going to be way more interesting. And like I say, everything's fine. I will see you all.
Thank you.